Hello everyone, welcome to Alberta-based AquaClim Solutions. We'll present a four-part series on the topic environment and floods. Series 1 will cover the topic on fluvial environment on socioeconomic factor. It will provide a general idea of fluvial environment or drainage basin influence on social and economic conditions. This presentation covers the topic on understanding what is fluvial environment, geomorphology, the types of processes a stream follows throughout its life cycle like erosion, transportation and deposition. Then we will see what are the fluvial environment and socio-economic conditions, anthropogenic impacts on fluvial environment. We will concentrate on the floods and explore the approaches of GIS in flood assessment, some of the models related to flood assessment, and how GIS is being used throughout the stages of such assessments. Fluvial environment is the environment created by fluvial activities. Fluvial is relating to or occurring in a river or processes associated with running water. It is also called geomorphology, that is nature and history of landforms and processes which created them by the rivers. Every river is a part of a larger system known as watershed. Drainage basin in a watershed is dynamic and constantly changing both in time and space. A watershed is an area of land that drains all the streams and rainfall to a common outlet. In fluvial environment, erosion, transportation and deposition by streams changes the land area. Local geology, physiography and climate determines the stream flow and sediment supply in a fluvial environment. In the fluvial environment, for study or modeling purposes, it is important to consider watershed area as a study area. Fluvial environment has a significant impact on the socioeconomic factors to the communities. Geology, land use, land cover change, and hydrologic controls are stressors that significantly alter the level of geomorphic change and sediment supply in a drainage system. Precipitation provides the energy of flow for the system and directly influences the balance between the flow and sediment supply, while anthropogenic factors can destabilize streams, leading to short-term or long-term adjustments in the stream morphology. Physical changes to streams can be caused by degradation, widening, aggradation, and planimetric form adjustments, all of which can be influenced by geology, hydrology, climate, and anthropogenic factors. Understanding stream morphology is essential for making informed management decisions, as it can affect flooding patterns, erosion rates, sediment movement, and deposition. To understand fluvial environment, it is important to have understanding of fluvial processes at different stages of the life cycle of a river system. Different courses of a river can be classified in three categories, that is upper, middle, and lower course. Erosion, transportation, and deposition are the three dominant fluvial processes constantly working with different intensities throughout. Erosion is a gradual removal of rock materials from the riverbanks and riverbed. Steep slopes are categorized by dominant vertical downward erosion, depicted by more number of first-order streams. There are four types of erosion processes within the river: hydraulic action, abrasion or corrosion, solution, and attrition. There are many erosional landforms created by the stream in the upper course, including potholes, rapids, waterfalls, gorges, interlocking spurs, V-shaped valleys. Fluvial transportation. It's simply the river load or eroded materials transporting from one place to another during its course, which is influenced by local geology, gradient, land use, soils, vegetation, and weather conditions. Processes where large boulders too heavy to be picked up rolled along the riverbed in the direction of water flow, called traction. Saltation occurs when small stones, pebbles, and silt bounces along the riverbed carried away. Minerals and other chemicals dissolve away as a solution. Suspension is the process where smaller particles are carried within the water by turbulent flow. Rainfall occurrence increases the energy of these streams, influencing bed, which resulting in more material transported by traction or saltation. In the fluvial processes, deposition occurs when the velocity of river decreases and unable to carry its load due to lack of precipitation, increase in evaporation, increased anthropogenic activities. Many deposition-related landforms created by the stream includes point bars, floodplains, back swamps, meandering river, oxbow lakes, salt marshes, alluvial fans, alluvial terraces, delta. Important watershed characteristics that influence fluvial deposits include basin area, discharge regime, sediment load, lithology, land use, land cover, drainage basin morphometry. Urbanization, maximum settlement, industries are the most important factors influencing the changes into fluvial regime. The relationship between fluvial environment and anthropogenic factors can be understood through the conceptual framework presented in the figure. Fluvial environment provides key resources for communities, including food and income from fishing and farming, and facilitates transportation and trade, especially in areas lacking other infrastructure such as roads and railways. In addition, it provides opportunities for tourism and economic growth. However, if not managed properly, it can cause harm to socioeconomic conditions through water pollution, degradation of resources, and disruption of water flow due to climate change or dam construction. These changes can damage transportation infrastructure and make it difficult to move goods and people. Furthermore, polluted and degraded water can also significantly decrease the attractiveness of an area, leading to a decrease in businesses and recreation activities and influence the health of the communities. Anthropogenic impact on fluvial environment is profound. Human actions can be localized, regional, or continental, influencing local area to the continental level. Natural, that's biophysical, and human-induced fluvial processes may also differ in the magnitude, frequency, and direction. Construction, excavation, hydrological interference, farming are some of the activities affecting directly. Indirect anthropogenic impact equally are serious concerns. Land cover modifications have accelerated erosion and sedimentation, triggered landslides and debris flows, changed river channel forms, and created subsidence. One of the planet's worst tragedies happened in the last decade in India in Kedarnath town on June 2013, which was triggered by heavy rain and cloudburst on the massive glacier lake called Charobari. It caused heavy landslides, soil erosion, where the upper part of the Kedarnath town washed off, and the town of Rambara vanished, affected 4,650 villages and more than 10,000 deaths. Unplanned, haphazard construction, mismanaged tourism, intensive mining in the fragile watershed were the major contributing factors led to this intensity and magnitude of damage. Recently, we have seen frequent occurrences of floods in the world. Some of the most notable flood events in recent years include the 2010 Pakistan floods, which caused the estimated $9.5 billion in damages and affected over 20 million people. The floods in China affected over 51 million people and causing billions of dollars in damage. In the United Kingdom, heavy rains and strong winds caused widespread flooding, leading to evacuations and significant damage to homes and infrastructure. According to data provided by the National Flood Insurance Program (NFIP) of the United States, Canada has been experiencing an increasing number of flood events in recent years. The provinces of British Columbia, Alberta, Saskatchewan, and Manitoba are prone to flooding due to their locations near major rivers as well as their high precipitation levels. The Hurricane Harvey in Texas, which caused an estimated $125 billion in damages and resulting in the death of 80 people in 2021, a word to mention. Geospatial technologies such as remote sensing, geodesy, photogrammetry, and computer science (GIS) has revolutionized the application of analysis in the field of fluvial environment assessments. Key features of this field include quantitative description of landforms, process modeling, form-process relationship investigations, links to climate and environmental conditions, statistical analysis, regionalization of field data, graphical visualization, and map creation. Visualization and landform classification, land surface and hydrological analysis, topographic change detection, process and erosion modeling, and hazard susceptibility modeling are all integral components. DM, LIDAR, drones, structure from motion, that's SFM, and SRTM are common data sets used in this field, supplemented by various types of image data. DEM derived land surface parameters include altitude, aspect, slope, and curvature. Hydrological parameters derived from DEM include flow direction, flow accumulation, discharge network, channel sinuosity, and drainage density of a catchment, with higher density indicating a more mature channel system, rapid surface runoff, and low infiltration rates or thin vegetation. For local study, aerial photos are still used, and high-resolution satellite images are used for mapping larger areas. Many satellites of various kinds orbiting the Earth providing data constantly. Temporal resolution of satellite images are very important for studying fluvial characteristics, features, and their changes over time. Unmanned automated vehicle UAVs and multi-copters are available at low cost and make data acquisition cheap and relatively easy, especially in remote areas and in the steep, rugged terrain where shadowing effects limit the use of aerial photography. Digital photogrammetry is a powerful method for extracting digital topography from overlapping images. Structure from motion photogrammetry (SFM) software calculates picture geometry, orientation, and position of the cameras toward the object of interest by matching common features in a set of overlapping digital images. All kinds of field and lab data can be imported into GIS for analysis. Data on surface material characteristics produced by sampling, covering, or near-surface geophysics, mapping data, as well as measurements of process rates, and lab data like sediment analysis or dating information can be combined with digital land surface data. Fluvial geomorphological mapping are highly complex thematic maps that combine various layers various geomorphological informations. GIS can be utilized to identify regions which are prone to flooding and to evaluate potential impacts of flooding in these areas. Maps and data related to flood risks, such as locations of vulnerable population and essential infrastructure, can be generated and analyzed with GIS. This technology can be utilized to assess economic, social, and environmental consequences of flooding in an area, as well as to identify strategies for reducing the effects of flooding. Furthermore, GIS can be used to develop models to estimate the probability of flooding in the affected area, as well as the vulnerability of the area to flooding. For instance, the Flood Vulnerable Index (FVI) can be employed, which considers elevation, the presence of protective infrastructure, and land use types. Let's dive into some of the models of flood assessment. For the flood assessment and forecasting, we use more than one model to manage, predict, report, and manipulate. A model is a simplified representation of a concept, phenomenon, system, or structure that is used to better understand and predict its behavior. Models can be used to represent physical systems such as a watershed. It describes how inputs such as rainfall are translated into an output such as flood levels. Hydraulic models are those used to simulate the flow of water and to predict potential flooding in a given area. Geographic information systems are used to create maps and analyze data related to flood risk. Statistical models use probabilistic characterization of historical data to predict potential flooding in an area. Remote sensing models use satellite imagery to detect potential flooding and to assess the impacts of flooding on a given area. There are many approaches of flood assessment. It involves risk identification by identifying areas that may be at risk of flooding and assessing the potential impact on those areas. Risk analysis is analyzing the potential impacts of flooding on areas identified as being at risk. Risk evaluation is assessing the economic, social, and environmental consequences of flooding in the identified areas. Risk management is developing the strategies to reduce the potential impact of flooding on the identified areas. Risk communication is communicating the potential risk of flooding affected communities and stakeholders, and risk mitigation is implementing the strategies to reduce the potential impacts of flooding on identified areas. There are various kinds of models evolved for the flood assessment. Some of the models are flood protection level (FPL), which uses elevation data to identify areas that are vulnerable to flooding. Risk-based vulnerability model, economic loss estimation model, displacement risk assessment model uses land use, population density, along with other factors to assess the vulnerability, potential impacts, and economic costs associated with it. This is the end of Series 1 of 4-part series, AquaClim Enviro Solutions. Thanks everyone who enjoyed this presentation. If you have any questions or clarification, feel free to write to us in the comment below.